Welcome back to my channel. Did you ever want to build your own database? No? Oh, okay. Then every time you use Google, YouTube, your hard drive, or do pretty much anything interesting on the internet, there's nearly certainly a B tree involved. So, let's talk about B trees. I'll have to get a bit technical here and there, but don't worry, if you don't understand everything, I'll break it down step by step for you with hopefully useful visuals. B trees or their derivatives are what power most of the modern world. Nearly all databases and file systems use them, and while implementing my own in-memory database for a game engine I'm working on, I noticed that it is surprisingly difficult to find good information on them. Now it may be that I'm just bad at finding such information, but I wanted to make this video so that maybe you might have an easier time understanding how they work. I won't show any actual code, but I will explain how they work so maybe someone else will have an easier time researching. Let's get the boring stuff and some terminology out of the way first. The degree or branching factor of a tree or a graph is the number of children each node has. A balanced tree is one where all the leaves are on the same level. The median is the point in the middle of your dataset if you sort it. The predecessor is the largest key that is smaller than the key that you're looking at, and the successor is the analog just for the smallest key that is larger than the key that you're looking at. An index is a thing that allows you to find some value by some key. For example, finding all the viewers that are not subscribed to my channel. If you like this sort of content and would like me to make more, subscribe and let me know what you'd like to see. A B tree of max degree k is a balanced search tree where each node can hold up to k-1 keys, but has to stay at least half full, and each internal node has one more child than keys. The structure of a B tree is the following. Leaves hold key value pairs in sorted order. Internal nodes also hold key value pairs in sorted order, and a list of children in such a way that all the keys are separators between the children, meaning that the left child of a key contains keys that are smaller than the key, and the right child contains keys that are larger than the key. And because internal nodes always have one more child than keys, there's always a right and a left child for each key. In general, all operations take O log n time, with n being the number of key value pairs in the tree. And yes, that does indeed mean that a B tree of degree 2 is just a self-balancing binary search tree. But then, one might ask, why bother? Why not just use a self-balancing binary search tree? There are two main reasons for this, and one is called cache locality, and the other is the way block storage works. Let's look at an analogy. Imagine how when you go to the grocery store, instead of just getting that one onion you need, you might get a bunch more and maybe some other stuff, so that you don't have to go to the store every single time you get hungry. In a similar way, when your computer loads data in your CPU cache, it will load an entire chunk, called a page, that contains the data you requested, assuming that you are probably also interested in data that is close by. This is called cache locality, and an example for that is iterating through arrays. This works similar for block storages like your hard drive. By increasing the degree in a B tree, we can significantly reduce the number of load operations necessary to search through it. Loading memory is by far the slowest part of the entire process. Let's talk about 3 operations necessary to make this useful: searching, inserting, and deleting. But first, we need to define a helper function, which makes reasoning about this a bit easier. Let keySearch of k be a function that returns either the position at which the key is, or the position where we would need to insert the key to keep the structure sorted. Now that we have the boring stuff out of the way, let's look at how we would search for a key X. Starting at the root, we use keySearch. If a key is in the node, we simply return the associated value at the position keySearch returned. If a key is not in the node, then we have two cases. Either we are in a leaf, then we know that the key does not exist within the tree. Or we are in an internal node, then we search the child at the position keySearch returned. That is really all we need to do. Inserting is slightly more interesting. To insert a key, we first use keySearch and walk down to the leaf where the key should be. If the key already exists, we choose to either do nothing or update the associated value. Otherwise, if a leaf has room, we just insert the key in sort order and we're done. If a leaf is full, we split it. We pick the middle key, the median, move that key up into the parent and create two nodes out of the left and right halves. Then we continue. If the parent is full, we split it too, and so on. Splitting can go all the way to the root, and if the root splits, then the tree grows by one level and stays balanced. That preserves all our invariants. Deletion is a bit messy and complicated. First, like usual, we search for the key to be deleted. There are two cases we have to differentiate. The target key is in a leaf or in an internal node. If it is in a leaf, we simply delete it from the leaf. If that leaf becomes key deficient, or in other words, does not enough key value pairs to preserve our B-tree invariance, then we will need to rebalance that tree starting from the leaf. I'll get into that later. On the other hand, if a key is in an internal node, we replace that key with a predecessor or successor and remove that predecessor or successor from the child. Ideally, we pick the child that does not require rebalancing if we delete that key from it. If deleting that key from it does cause a leaf to become key deficient, then we rebalance that tree from that leaf. Okay, so how do we deal with key deficient nodes? There are two options. Option 1, we have a sibling that isn't at the min size. In that case, we steal a key from a sibling, or rather the parent donates the separating key and replaces it with the appropriate key from that sibling. If the node we stole from is an internal node, we also have to move the orphaned child. This operation in trees is usually referred to as rotation. Option 2, we have no such sibling. Then we merge the node, the parent separator and sibling into one node. Remove the separator from the parent and replace the two children with a new node. If this causes the parent to become key deficient, repeat with the parent until we reach the root. If the root node loses all of its keys, shrink the tree by one layer. And now we come to the part that is basically not mentioned anywhere, and that is how to handle duplicate keys. So, for example, if we wanted to index the color of birds, then we could only ever index one blue bird at a time. This is obviously not very useful and requires that we modify the tree. Instead of storing the key, we can instead store a tuple of a key and discriminator. And the discriminator is typically the primary key in databases. Even if you don't have one defined, most databases will create a hidden one for you anyway. Not just for this reason, but this is one of the reasons why it does it. The sort order is then determined first by the key and on collision by the discriminator. Insertion and deletion work exactly the same way, except that you also have to provide the discriminator, which isn't an issue in databases because they know the record's primary ID. Searching becomes a bit more complicated, since it is now possible that if we find a key, there's also a duplicate key to the left or right of it. If we define a different key search function, duplicate key search, that instead returns a slice, start and end, with start being the first occurrence and end the last occurrence of this key, then this makes our life a bit easier. So if we are in a node that is a leaf, then we can return all the values between start and end. If the current node is an internal one, then we return the search result of the left child of start, then the search result of the right child of start, then the value to the right of start, and so on and so forth until we end up with the child to the right of end. This will return the keys in sort order. So with this tweak, B-trees can actually handle duplicate keys, which is essential for any real database, because you'll have often identical values indexed. And that's it for B-trees. How they search, insert, delete, and even handle duplicates. I hope you found this as interesting as I did, and if you want more breakdowns of data structures and/or technology, let me know in the comments.